Hello everyone and welcome. Today we are conducting a technical review of Thevenin's equivalent. The power of this method lies in its scalability. It applies for large systems such as national grids or small circuits, small DC, low voltage circuits such as those in your cell phone. So from the point of view of interconnected grid, all we need to know in the substation is an equivalent source and equivalent impedance. We don't need to know every connection and every transformer in the system. So the main purpose of this method is to simplify complex circuits into simple ones to aid in the steady state analysis of the effect of the substation or any circuit on a given load. Of course, if we are going to do a short circuit analysis, we need the short circuit capacity of the substation as well as the reactances and so forth. But of course, that's another subject altogether. So let's illustrate this method by looking at this simple circuit, which is composed of a 10-volt DC source with a number of resistors, as well as 1 nanofarad capacitor, and then some load. Of course, don't look down at these simple resistors, because even distribution and transmission lines, as well as generators and motors, are modeled using resistors, capacitors, and inductors. So let's look at the equivalent circuit to start with. Now, the Thevenin equivalent for that composite circuit is going to be a Thevenin resistance of 54.5 in series with the load, and a voltage source of 5.45 volts. How do we get these values? Is by applying 3 simple steps. The first step is to remove the load, and you notice also here that the capacitor has disappeared, because the capacitor in a steady state DC circuit looks like an open circuit, so we don't need to keep it. And now we can compute the voltage across the open terminals, and that will be our Thevenin voltage. In doing that, we can see that this 200 ohm and this 300 ohm resistors are in parallel. So what we can do is find the parallel equivalent, which simply comes out to be 120 ohms. And then with a simple voltage divider rule, we can find that the voltage across these 2 terminals, which is the same as the voltage across this 120 ohm resistor, basically is 5.45 volts. Now the third step is to zero the sources. Of course, here we have a voltage source. Zeroing a voltage source means replacing it with a short circuit. If we have current sources in the circuit, zeroing current sources means replacing them with an open circuit. So after shorting the voltage source, we end up with this 100 ohm being in parallel with the 120 ohm resistor. So again, with a simple equation, we can find the parallel equivalent, and it comes out to be 54.54 ohms. So here's again the equivalent, Thevenin equivalent for this example circuit. And the reason why it is equivalent is because, again, the current through the load resistor and the voltage across it must be the same for the two versions of the circuit. So in order to verify that, let's assume a load resistance of 100 ohms and then compute the current through the load and the voltage across it for both versions. Again, you should be able to do this and verify that the voltage across the load resistor comes out to be 3.529 volts, and the current through it is 35.294 milliamps. Of course, notice there are very small discrepancies between the two. They are essentially the same, and I will leave it to you to figure out why do we have these small discrepancies. These are simulations, but they are very easy to verify by calculations. Okay, so summary of the steps to compute Thevenin equivalent. The first one is remove the load. Second step, compute the voltage at the load open terminals to obtain the Thevenin voltage. And then zero the sources, meaning to replace voltage sources with a short or replace current sources with an open circuit. And then from those, you can compute, after doing that, you can compute the Thevenin resistance. Any questions, please write them down in the comments. I'll be happy to respond. Now this is a simple exercise for you. I've just changed the values for the source, the resistors, and the capacitor. And then it's your job to verify that the voltage or the Thevenin equivalent looks like this. Assuming again that the load resistance is 100 ohms, verify that the two circuits will give you the same current through the load resistor as well as the same voltage across it. And these are the values so that you can verify whether your work is correct or there is some discrepancy. Okay, I'll leave you with some questions. Suppose the circuit contains an inductor. How would you deal with an inductor in DC steady state situation to compute the Thevenin equivalent? Second question is, suppose the source was AC instead of DC. How would you analyze the circuit to find the Thevenin equivalent? Of course, you need to look at S-domain analysis, which is a topic for another discussion, but I'll be happy to hear from you. Okay, thank you for watching, and hope this was a useful review for this powerful theorem.